Hello everybody, my name is Adam Drewery. I'm an embedded electrical engineer at Drewery. Today we're going to talk about Agile hardware leveraging open source designs. So at a high level, we're going to talk about some of the challenges of IoT development that we're trying to address with this process. I am personally an electrical engineer, so mostly we're going to be focusing on electrical engineering in this talk, but I will talk a little bit about some of the other areas. We're going to talk about why you should consider using Agile IoT development or Agile development for IoT projects. And then also talk about some of the ways you can really view hardware as code to help fit it a little bit better into the process. We're also then going to kind of round out with a few examples of how you can use some open source hardware and firmware to really shorten the design time. So one of the biggest issues with any project that involves hardware is it kind of inherently just falls into this waterfall design method. The firmware doesn't start until they have the hardware in hand, and that, to me, that's a little bit of that's the wrong way to go about it. Because frankly, hardware without firmware is boring. So if you have a circuit board that is meant to have firmware running on it, why not consider what the needs of that firmware are in as much detail as you can while you're designing the actual hardware. I think it just generally lends itself to a much more smooth process all the way throughout. The other thing is that it ultimately lengthens the feedback loop. So if you don't do, the hardware has to be done, then the software or the firmware gets done, and then they can start talking to whatever backends or anything like that you're going to have to communicate with. It's a long time. Sometimes it's 6 to 12 months before you can get the first fully functional prototype. The other issue is that hardware costs money. Raw materials costs, we're looking at generally we'll do for a round of 10 prototypes about a week turn time. That's $5,000 or more just in raw materials costs. So if there are any issues, it's really an expensive thing because it's not just the materials cost, it's also the time spent and potentially debugging and waiting for another round of hardware. And also, frankly, statistically speaking, 10 is not very significant. I consider it kind of the bare minimum. So if you can make 10 of something work, you can probably scale up to larger numbers. Moving on to certifications, this is something that I think is often overlooked, even by hardware engineers, frankly. When you deploy hardware to a location, it has to be deployed or compliant in whatever location it's deployed or whatever context it's deployed. It also is important to keep in mind that the firmware can actually alter the hardware performance. And then if you fail here, then you're looking at months of delays in your project. And this is generally when you think you're at the finish line or almost at the finish line. It's the worst time to have something like that happen. I strongly recommend, this is from personal experience here, pre-compliance testing is basically you do the compliance testing, but they help you fix any issues before you go to the final compliance test. And that gives you the opportunity to actually verify your design is going to work before the test lab would just reject it and send it back to you, and then you have to fix it, send it back, and it becomes a cycle. That's where the months come in. Anytime I have done pre-compliance testing in my career, I have gotten through the compliance test first try. Anytime I have not, it's taken months. That's just generally how it goes. And then we're going to talk a little bit about manufacturing is also another thing that I guess is left until the end. People don't really think about how do you actually make this thing until you've got all the pieces in hand and you've assembled the first few units. And then you also have to consider how do you break that part down into these smaller pieces that you can then put back together and really kind of go through more of an assembly line process. Then you have to define, okay, we've got these components coming in. What are the inspection criteria? How do we tell whether or not something has been successfully made when we first get it and then successfully gone through the provisioning process? This is often handled by QA, and we actually do involve them in our Agile process. And we'll talk about that here in a few slides. So Agile development actually, the intention is really to focus on vertical slices that deliver higher level features. So let's turn on an LED with an app. So that whole process from pushing the button in the app all the way to the LED actually coming on and what it actually looks like, that matters. And that's the experience of using that product, or at least that portion of that product. Each team member on your product team has to deliver something in order to make that actually work. And then you also have to consider, it's best to consider earlier on at the same time you're designing it, what are the manufacturing and certification issues that might arise. We were actually talking to a potential manufacturing partner at one point, and they mentioned another client of theirs actually wanted to use or add a nightlight into their product. When they found out that the nightlight caused extra certification to be applied, they actually just removed the nightlight feature. And it's super important to know that stuff before you're at the finish line and about ready to go to production. And then you realize you have to spend a bunch more time to fix something. Agile really forces you into a shorter design cycle, and that's to focus the team's efforts to really deliver that one feature, whatever that feature is. It really strongly encourages breaking this bigger, larger product down into the smaller pieces that actually can then just be put back together and built up. It also forces you, or not forces you, but there's a lot of emphasis placed on shipping something that works and then iterating on that working design. I can tell you from my 8 years of experience, very few designs are ever correct on the first attempt. It's also important to keep in mind that with this process, when you're just prototyping, it's not meant to be a perfect representation of that end product. It's meant to simulate what that end-to-end experience is like. And that will ultimately allow you to get some clues, at least, as to whether or not we're actually headed down the right track. It's also important to keep in mind that when you do have that hardware, you can actually modify it. So we do a lot of hacking on circuit boards just to make sure that we can test out every bit of firmware that we possibly can. And ideally, you make all of your peripherals work before you move on from that first design. It also, Agile as a whole, really looks to remove uncertainty from a design. And uncertainty really, in my experience, comes up when you have an interface between two things. So for electronics, obviously, there's two circuits that get interfaced. But other parts of the project team are going to have an API where maybe the firmware has to talk to the backend, and everything better be right, because that's probably going to be happening over like a cellular connection, or could be happening over cellular. Every bit of data counts there. So everything has to be right. Otherwise, it's kind of hard to tell what actually is being said sometimes. This Agile also encourages flexibility. It's okay that things change. In fact, that it's encouraged to change things, especially if you've made a mistake and you learn something doesn't work. Then adjust away from it, and you can do that earlier in the project rather than waiting until the very end. This ultimately leads us to the solution we want, rather than the solution we thought we wanted at the beginning of that project. And the last and probably most important for us is we're a contract engineering firm's transparency. So we have daily meetings, generally 15 to 30 minutes with clients, and then we have weekly planning sessions. They take part in all of these things. And ultimately that provides them visibility of the progress that's being made and allows us to direct where we're going to head forward. This helps them establish trust, or this helps to establish trust with their clients, and it makes them feel like part of the team. And ultimately that helps when things go wrong. So it's much easier to approach a difficult conversation when you feel like somebody's on your side. So I mentioned that interfaces cause uncertainty. So in electronics, connecting two circuits together is really where that comes up. So you have things like loading, or a default pin level of one of them causes the other one to come up in a different mode that you don't necessarily want to. There's really a lot of chances to connect things incorrectly. So we're looking at a little bit of an example of the schematic here. This is the top level sheet of a hierarchical schematic. Each green line there is an individual connection between the microcontroller and something else. And then the blue lines represent groups of at least 4 or more. So as you can see, there's hundreds of chances to make a mistake. And just in terms of when I design something like this, just on a single circuit board, I typically go through 5,000 pages or more of documentation. So average paper thickness of 0.1 millimeters. If you print double-sided, that's 250 millimeters stack of papers, or almost 10 inches tall. So there's a lot of chances to miss little details. So it's really important to drive out the uncertainties as early as you can, especially before you get to something like this, where you're making the actual PCB layout. If each line isn't connected correctly, or to the right spot, or you know, maybe somehow you missed it going through another connection or something. I don't know. But if that's not all done correctly, there's a good chance it's not going to work. Now, in this particular image here, these squiggly lines, this part's super important. These are DDR3 RAM layout or lines, comms lines. This runs at about 800 megahertz. What this ultimately means is that within 2 nanoseconds, or 0.000000002 seconds, 2 bits are going to be clocked back and forth between those two devices. That means that those lines have to be within a few tenths of a millimeter in order to guarantee that everything gets there at the right time. Now that takes a lot of design time and effort to make sure everything is correct there. You also deal with like board stack ups and all kinds of other stuff. Easily 2 to 3 weeks just on that little portion of the circuit. And if it's not right, when you get your hardware, your microcontroller probably isn't going to talk to your RAM, and then your whole device isn't going to work. And then because they're such high frequency, they're really sensitive, and so you have to have much more expensive and advanced equipment to actually debug them if you're in that kind of situation. Suddenly getting that wrong costs you another week or more, and the cost $5,000 at least of a new round of circuit boards. That's really hard to deal with. But much like interfaces between circuits cause uncertainty, similarly, interfaces between your different parts of your design team will cause uncertainty. So I like to think about the team as a wheel. And in order for the wheel to roll, at the risk of saying something incredibly obvious, it's got to be round. And if those interfaces aren't right, then the wheel becomes lumpy or incomplete, and you have a very uncomfortable ride. So kind of starting to bring this wheel together, you have to have something sold in order to justify bringing a product team together. And then you have to have, especially for us as we're also a 100% remote company that is a contract engineering firm, accounting, resource management, logistics, all of those things are super important. Engineers can do them, but it's probably better to have them, flipping bits in firmware and routing circuit boards and doing the things that they really like to do that, frankly, most people don't want to. And then, frankly, one of the, I guess, unsung heroes often is a PM. Someone has to herd the cats. Engineers they can get all over the place, so someone has to keep herding the cats. So looking at the wheel, each of these individual slices here, at the top you see the UI UX team, the user interface and experience. So this is what the end user is actually going to interface with. The success of or failure of some feature is going to start and end there. Can you still hear me? Okay. Let's see, where was I? Top of the wheel. Okay, I'm ready. Sorry. All right. So going clockwise around the wheel, the mobile and the web, that's your web interface or your app. They're responsible for making that user interface actually do what it's supposed to do. And then that kind of rolls down into firmware and software. There's probably some backend stuff in between there. That the firmware and software that's really responsible for taking the interface commands and sending them down to the hardware, and then taking the hardware commands or data and typically sending them back up to whatever the remote interface is. Then you kind of keep rolling around the wheel here into electrical. This provides, ultimately, I just provide a platform on which the firmware actually makes the magic happen. Once this is done, we don't touch it, right? That's generally the best thing you can do, again, because of compliance and things like that. And then going around to mechanical, you typically don't just give somebody a bunch of circuit boards and say, here you go, You package them nicely. And then this is the hardware experience. This is the look, the feel, the sound. If you taste, smell, I don't know what you'd be making there, but something like that, right? All of those things are super important, and they have to, again, they have to turn on the LED. All of that stuff has to kind of make sense together, and it has to look the same. Otherwise, that experience feels disjointed. And then the wheel is bound together by the QA department. These jerks are always trying to break your stuff. More importantly, or more correctly, they're actually preventing everything from breaking once it's actually out in the field. And these guys are truly these people are truly the most underrated parts of a team for IoT success. They're working at a higher level. They're making sure that the things actually, there's an independent check on everyone else's designs. And in particular, firmware or software, it's easier to do test-driven development there, but in electronics, it's not quite as straightforward. They can serve as a form of test-driven development, essentially, and help you define the test your circuit has to pass. All right, so another round thing is cake, except this time, let's break the cake down by layer. As an example, let's say someone comes to us and says, we want the following peripherals. I want a sensor that detects a thing, probably a gas or something like that. And then they want some kind of indicator of this alarm status. So maybe an LED. There's an alert via text. There's a status update somewhere on a UI, maybe a place to clear that stuff. So let's think about what these team members, these slices each have to do. UI, UX, they have to come up with that interface. They have to also help mechanical kind of define what that look is and make sure that it matches with the remote interface. Obviously, mechanical is responsible for dealing with the physical experience of the project or the product. The electronics has to fit in the mechanical packaging, and then it's basically just, it's again a platform that hosts the firmware. The firmware then has to pass the commands and info back and forth between the web and the servers and the hardware. The mobile and then the web team, they obviously have to implement that interface so that people can actually do whatever it is they need to do remotely. I'm going to focus specifically here on the electrical. So in the image, most people probably think, oh, it's a light and a sensor, whatever. Well, what about powering that stuff? How do you connect to the internet? How do you interpret those commands? So suddenly you don't just have a sensor circuit and an LED, you have a microcontroller, you have some form of circuitry to get you connected to the internet, and you have power. That's now not just that simple, right? So you really have to understand how these layers fit together and when these layers are going to cause the other layers to have issues, essentially. And keep in mind, they're not also going to always be equal in thickness or the amount of work they have to do. So let's loosen up our belts a little bit here. Oh man, after that cake, got to loosen up your belt, right? It's also a pandemic, so let's give everyone a little bit of a break here. What I'm really getting at though is you want to give yourself flexibility to change. In this particular project, we were at this point and we realized, man, we're going to have to put a display right here. That's going to cause problems with all those parts right there. So we decided to change. We moved the circuitry to a different board. We left that other stuff, the LEDs and all those other things on that other board. And we just interfaced those two boards that actually wound up leading us to the solution that we really wanted. Again, that is so much more important at the end of the project, I think, than having everything done exactly on budget and exactly on time. I think people are happier when they get the thing they want. But hardware is hard. Literally. Hilarious. I should point out I do have a kid, so I'm okay. I'm allowed to do that. I think really hardware is hard though, because it's not considered holistically. So this tends to hide some of the unknowns or uncertainty. Oh, that dirty word, uncertainty. And what it actually takes to make something work. So something that we're going to kind of pivot into here is how to view familiar circuit building blocks as things like functions, classes, and libraries. So here you see a hardware function that is a power converter. So maybe we would give it an input power. We would give it the maximum output power and maybe a target efficiency. Or maybe we have a sensor that has a temperature sensor. Oh, excuse me. Giving you a sneak peek there. We have a sensor of type temperature that you call sensor read function, which is basically an analog output signal from a temperature converter. Or maybe down on the bottom right here, we have a sensor configuration to set this proximity detector to interrupt at a certain, when an object is within a certain distance. Or maybe you want to signal condition stuff. So here we're telling it, hey, I want a low pass filter with this cutoff frequency. Or maybe other ones could be like an amplifier, and you tell it I want an inverting or an integrating or a summing and maybe a gain. So there's lots of ways you can really start breaking things down, but as the circuitry becomes more complex, for example, like a microcontroller, they're really starting to become more like a class. You have different properties that enable specific functionality, but you don't have to always use them, right? You always have your UARTs, your I2Cs, your ADCs, but you don't always have to use them. Circuit functions, also the ones we just talked about, those can similarly be thought about as classes. And then ultimately what you do, like the schematics, I probably should have added it back here, but you saw boxes connected by lines. Those boxes are these classes and functions essentially, and then we organize them in a hierarchical schematic and connected them together. So when you get to something like a completed circuit board, in this image here, this is a BeagleBone Black Wireless, it becomes something like a library. So a dev kit will provide you the access, and again, at the risk of stating something obvious, the dev kit is a PCB, and it will allow you the access to access the majority of the microcontroller functionality. We at Very are particularly fond of the BeagleBone series of single board computers. They are built on the AM335X from TI. They're a good general purpose industrial microcontroller. Most importantly, they have NERV support. So NERVs is an embedded Linux system that's built on Erlang Elixir and runs on what's called the Beam virtual machine that actually runs on the microcontroller. And it's really fault tolerant, really meant for embedded applications, super small footprints on the orders of tens of megabytes for a complete embedded Linux distribution. Also, if you connect it up with NERVs Hub, you can actually do download resumption of firmware updates. So let's say you're bandwidth limited somewhere and you cut off halfway through your firmware update. Well, it'll just start you off where you left off rather than making you download the whole thing again. That's going to be that's a very big thing for a lot of potentially very remote distributed systems. And that's also really difficult to do in embedded C. And lastly, it's certified, so it's FCC or CE certified North America and Europe. That gives you a higher confidence that you're going to actually be able to get through compliance yourself when you actually have your hardware in hand. So here we're looking at the import of just raw Gerber files of the BeagleBone Black. The BeagleBone Black Wireless, the source files, the schematic and the circuit board files, those are available in EUCAD. That's really clean and easy to import into KiCad. KiCad's didn't really even talk about it, but it's free open source ECAD tool that we actually use. A very, very awesome tool. We like it a lot. The BeagleBone Black is only available, however, in ORCAD. That doesn't cleanly import, but into KiCad, but you do again have these Gerber files that I'm showing the import to. So let's take a look at these squiggly lines here. That's great. We have our RAM layout essentially just by importing the Gerber files. Now, kind of need a little bit of cleanup here. Hey, there we go. Just to point out, it was rotated, so that's maybe looks a little weird. But ultimately, that RAM layout was done in less than a week, rather than I mentioned earlier that could take 2 to 3 weeks to get that layout done. The other thing this allows you to do is start to validate potentially very complex interfaces. So in this example here, you can see you have a 16-bit RGB interface. On the left, there's a breadboard implementation of it. On the right, there's actually a Volterra circuit board, and we'll talk about that here in a second. Ultimately, that allowed us to validate a 16-bit RGB interface before we ever actually ordered hardware. That's super important to know, because then you don't have to mess with that, and it's one less thing to debug essentially. It can also be used to test errata fixes. So that's essentially a bug in the silicon itself. So coincidentally, there is actually an errata related specifically to the RGB interface on the AM335X. So ultimately, on this particular product, we did go with a different screen, but we had that, both of those interfaces were validated before we ever ordered hardware, and we knew it would work when we got it in hand. And just at a higher level, you can also just any new peripheral. So in this case here, we're looking at the red circuit board. It's a CC1310 Launchpad from TI, and that's interfaced there with a Digi modem. I really want to give a shout out to manufacturer dev kits. They're super important, probably your best bet if you're doing this kind of interfacing and prototyping, because it's hardware that's known to work, which eliminates uncertainty. Ugh. But lastly, it provides a point of comparison when you're debugging your custom hardware. And I mentioned the Volterra a few slides ago. This is a Volterra printed circuit board. So it prints conductive ink. You can then put solder paste down, and then it'll actually reflow the stuff on there. You can have a design printed and assembled in less than 2 hours. That obviously you have to do the design work, but less than 2 hours to get that circuit board done. And that allowed us to start validating that LED driver there that we actually wound up using in this product. It's really ideal for simple test circuits. You don't really want to be making a lot of stuff with it. That's not what it's meant for. The big picture here is that it gives you confidence. We knew, like I said, that RGB interface was done correctly. We knew this was connected correctly, and that we could connect multiple of these chips on the same I2C bus. And that gave us a lot of confidence in our design. So then when we got our hardware, it just works. Now, I say that because I didn't have to write the firmware, but I just had to couch that. But yeah, thank you.